Hi there. I'm going to do a run through today of gravitational fields, mainly geared towards AQA A-level physics, but physics is physics, so sure it could be applied to teaching or learning in other A-level courses. It's in the fields topic, so fields will be gravitational fields for AQA, and then electric fields, capacitors, and magnetism, magnetic fields, and electromagnetic induction. So probably the toughest area of A-level physics most students find. So let's get into it. So, first of all, we need to talk about the force itself. Gravitational force, attractive force. When you come on to electric fields, electric forces, they can be attractive or repulsive. And it's to do with the masses, whereas in electric fields, we'll find it's to do with the charges. Weight's the name given to the gravitational force exerted by a planet or moon on an object. And by this stage, students should be pretty familiar with the difference between weight and mass, hopefully. Gravitational field itself, sometimes you get awkward questions where you have to describe what a gravitational field is. So a region or volume within which an object experiences a non-contact gravitational force. And two different types of field. Essentially, I suppose every field is radial, but on a small scale, say in the size of the room that I'm in at the moment, the field would look pretty uniform if you could see it. So that's what's zooming in there in that little bubble there. There's quite a lot of assumptions in this topic, and it's grossly simplified for A-level compared to how complicated it is in reality. And gravitational fields can be represented by lines of force, so arrows showing the direction of the force, and line density increases with the strength of the field. So hopefully so far so good with that. We talk about these radial gravitational fields then. One of the big assumptions that we use is we assume that everything is a point mass, essentially, and the same with charges. So planets are not uniform, planets are large as well, and stars, but we are really assuming a point mass. And I'll talk later on about when you talk about little r, what does that mean in the equations. Technically, it's the distance between the centers of the objects, which sometimes is important if the objects are quite close and they're compared to their radius. So the field lines go inwards. There's symmetry involved there, but we obviously know that planets are not spherical generally, okay? The Earth's an oblate spheroid, so there's quite a lot of approximation involved here. The field around a uniform sphere there, we're saying is like the point charge uniform field. Radial field being uniform in a way that it's distributed. So the field lines always point inwards to the mass. So it's a bit easier than electric fields, which depends on the nature of the charge. Now, field lines. Increasingly, AQA are asking students to interpret field line diagrams, maybe draw equipotentials or draw field lines given the other. And so worth having a little focus on this point. When you talk about field lines, between two masses, there will be a neutral point between them. If the masses are the same, which happens in a lot of same size in a lot of questions, then the neutral point will be in the middle. In this case, the Earth has got a larger mass than the Moon, so the neutral point where the forces cancel will be closer to the Moon there. And you can see that if you had to draw this in an exam, there would be marks for the arrows going inwards to the planet and the Moon, and there would be marks for more field lines coming into the Earth, perhaps, and then the neutral point being closer to the Moon, I imagine, if that came up in an exam question. So that's the lines of the gravitational field lines. So field strength, little g, so we can use F equals ma, essentially rearrange it. So g is the force over mass. And in terms of nomenclature, I prefer, instead of using m1 and m2 in this topic, I prefer using big M and little m, because I think it's less confusing or not ambiguous at all. So for instance, some students, there's a few equations for gravitational field strength, and students sometimes get confused about which one to use. So let's put the full slide up there then. Whoops. So field strength is equal to the force that acts per unit mass, or force per unit mass. And this unit mass, or per kilogram, is going to come up a lot in definitions. So it's a vector, same as the forces, and the units of it are newtons per kilogram, and there's a little slide later on talking about the two G's, gravitational field strength and acceleration due to gravity. So on Earth at sea level, the average value is that 9.81, varies quite a bit depending on where you are. Top of a mountain and things like that be less. And the moon is about 6 times less, but in no course that I've heard of, you have to actually know what the value of G is on other space objects. Just useful to know. Now, also, when we're talking about numbers like this, it's worth emphasizing that in AQA, for example, I'm sure in some of the other exam boards, some data is given to you in the formula booklet. So the mass and the radius of the Earth and the Sun is given in the AQA booklet, so they'll assume that you're going to use that and know where it is. So in case students worry that there's too many variables to work out in an exam question. So in terms of, as I said, G's, you don't have to know the value of little g on different things, but it's useful to have a little look and discuss with students. Jupiter, for instance, a lot of students guess it would be hundreds, but I have to point then out that Jupiter is not as dense generally as a solid planet like the Earth. I think all of the gas giants have thought to have rocky cores, but not particularly large rocky cores. Most of it's gas. And so that's why it might not be as high as people might guess, students might guess. I think it was agreed in a conference many, many years ago, little g to something like 5 or 6 decimal places, because it does vary. You know, it isn't a number like pi, there's an irrational number or anything going to go on forever, and it isn't an exact number. So it was decided, I think, at a conference many years ago, what the value would be. I think just 6 decimal places, but at A level, all of the constants are all given to 3 sig fig, really, generally in the booklets. So now I sometimes start off with Newton's law of gravitation and then go into field strength. Okay, but so Isaac Newton came up with his theory of gravitation, and the essentials are that every particle of matter in the universe attracts every other particle with a force, and these are the main points. It's really easy to trip up on these. The force is directly proportional to the product of the masses, inversely proportional to the square of their distance apart. Now, the main slip-ups here are students often forget product. They might say, oh, proportional to the masses, and they may not say square of the distance apart, or they might not say inverse or something like that. And all of these things are probed in exam questions, and you have to get all of those bits right to get the marks. And if you write that out mathematically, that's what you get. And now here, it's broken my rule of using big M and little m here. It's using M1, M2, but if you choose SI units, we can make that into an equation in a second, and you can see that's an inverse square law when you got it. Let's get to the equation bit, which is, I think, on the next page. But this one defines that M is the masses and R is the distance apart, distance between their centers. Technically, I think, if you want to be exact, really, okay. Because some questions, you have to take into account the radii of the objects as well as the distance from their surfaces. So if you insert the constant of proportionality and use the right units, then you get this equation. F equals big G, where big G is the universal constant of gravitation. M, or big M times little m, I would prefer, over R squared. Now, I've quoted their big G to more significant figures than is in most formula booklets. The students will be using 6.67 times 10 to the minus 11, with quite a lot of other units attached to it there. So it's a universal constant, and it's been measured many times over the years. It's a very small number, and that's really important. Even at GCSE, sometimes I put this equation on the board just to explain that the reason why we don't get objects flying towards each other gravitationally on Earth, because this constant's tiny, 10 to the minus 11, whereas the equivalent constant for electric fields, which you could call K, or 1 over 4 pi epsilon naught, that's 9 times 10 to the 9, I think, if I remember correctly, so a huge difference in size. So on Earth, the only gravitational force that's significant is to do with the fact that the Earth is beneath us. So one of the objects has to be at least a moon size, probably, really, for the force to be significant. So here's a little bit of information about measurements of G over the years. There's a really good video on 60 Symbols, I think it is, the channel on YouTube, where some staff from Nottingham University talk about Cavendish and his measurements. Cavendish is quite an eccentric character and did loads of really important work but never published it. And they asked an exam question a few years ago based on the Cavendish experiment, definitely worth looking into. But he measured big G to fairly close to the value, really, considering the time, and he did it in a big barn on his land A really interesting video, that is. I'll try and put a link to it in the description if I can. So often it's worth asking students to work out what is the force between two students sitting, a meter apart. And it comes out to be such a tiny number, okay? 10 to the minus 7 newtons, so pretty negligible, really. Now, this radial field relationship between little g and big G is important. Generally, you don't hardly ever have to use the equation little g is big F over little m, really. More often than not, you substitute in, you use this new equation that's going to come up, the radial equation. So you substitute in for Newton's force into that equation, and you get little g is gm big M over r squared. Now, the reason I like using the big and little m's here is it's clear what's happening. So you could have a question about an astronaut above the Earth or something, and then you might use, if you've given the mass of the astronaut, you might use g as F over m. But more likely, in most questions, you're going to have the mass of the large object, could be the planet or the star or something, and so it's more likely that you're going to be using this equation. So little g is big G m over r squared. Now, all the equations are very similar looking in this particular topic, so it's worth writing them out every time, really, and just having the formula booklet close to hand, students, so that they're familiar with the equations, what's given to you. Almost all the equations are given to you in AQA in this topic, apart from 2 or 3 or really, okay, and I'll accentuate those when we get to them. So here's an example here of calculating the mass of the Earth. So as I said earlier, I think those two constants there are given to you, and I think it's more precise than 6,400 in the formula booklet. So you might get a slightly different answer if you use the formula booklet there. So around 6 to the 24, but that's given to you in the exam, so this wouldn't be an exam question. The Earth's mass is given, and I don't think it does come out to be that. I think it's 5.99 or something times 10 to the 24. Worth having at some questions, or looking at some questions about field strength at various positions on Earth and maybe the space station, because some students are under the illusion that there's no that G is 0 on a space station, which you will find it isn't. So on top of Snowdon, roughly it comes out to be 9.77, Everest 9.74, and then on the International Space Station, using that data anyway, 8.97. So I think often students are surprised it isn't significantly smaller than that. But the International Space Station isn't that far away from the surface of the Earth. Now, I put a slide in here a few years ago because at AQA, anyway, in the AQA exam board, sometimes you come across a bit of a tougher question. If you see the word density in there, then you can't assume that there's going to be a linear 1 over r squared relationship between force and field strength and the distance. So this is how I could write this out, but I can't. There's no facility to write it out here. But the equations change. If the word density appears in one of these gravity questions, then you can probably bet your bottom dollar that you're going to have to try and get these equations at the bottom. So the F equation, the force equation, changes from gm over r squared. It changes to 4/3 gm rho pi r. So it's a linear relationship in r. And the same for field strength. So all you're doing there, you're replacing one of the m's in the force equation with density times volume, so rho times volume, and we're assuming a spherical geometry here, so 4/3 pi r cubed, and there's an r cubed in the numerator, and there'll be an r squared still in the denominator, so some of that cancels and you're left with a linear relationship in r. So just bear that in mind, that it doesn't come up that often, but when it does come up, I think it's one of those kind of questions that isn't answered very well by students. So if you can do that, or if students can answer those questions, then it's a real bonus for them. But that's what you're doing, really. You're just replacing one of the m's in the gm over r squared, or gmm over r squared if it's force, with rho times v. We're using a spherical volume, and I think the volume of a sphere is given in most formula booklets. Now, I put that there because the next slide is a graph of g against distance from the center of the planet, or whatever you're talking about. Now, the straight line shown there, it doesn't really come up, I don't think, in many exams, but that's a linear relationship, and it's a massive approximation. But that's the reason, that's where that comes from, and it's assuming the previous slide, assuming uniform density, which is absolute rubbish, right? The Earth isn't uniform density throughout it at all. The mantle, the core, and the various parts of the core. So that is quite an approximation. That linear relationship there. But beyond that, then you get a 1 over r squared. So inverse square law. I know up until now I haven't talked much about the inverse square law, but inverse square laws appear in many areas of physics, and they're really important. Potential is where students often struggle. I think the first bit. I should say at this point that if you're a teacher or a student of OCR, I think the previous equations got minus signs in front of them. In AQA, they've chosen a lot of the time to talk carefully in their language, and they talk about the magnitude of G and things like that. So they've removed the minus signs. The only thing in AQA that's got a minus sign is potential, or things related to potential, like potential energy. So just bear that in mind. Dependent on the course that you're doing, some of these equations might have minus signs in front of them. So the potential, this comes up as a definition frequently. It used to be worth 2 marks in AQA, but I noticed sometimes now recently it's been worth 1 mark, which is a bit weird. How you change the marks for exactly the same question. And it's the work done, or work done required to move a kilogram from infinity to the point. So there used to be a mark for saying the work done in bringing a unit mass or kilogram, 1 mark, from infinity to the point, 2nd mark. So what does that mean, infinity to the point? Well, the gravitational potential is defined at infinity to be 0, and it gets a little bit confusing here often for students. So I normally draw on the board, I draw a planet, and then I go off to the right-hand side and to where infinity might be. And I say, look, it's 0, the potential at infinity. And I say, okay, a certain time later, the object's moving towards, being gravitationally attracted towards the planet. And we're talking about an isolated system here. And so I say, what's happening to the kinetic energy? Well, the kinetic energy will start increasing as it's being attracted towards the planet. So overall, the energy must be constant. So what's happening to the potential energy? And students will hopefully then say it's decreasing. Oh, but we said it was 0 at the start. So if it decreases from 0, it must be negative. And that's one explanation about why you have negative potentials. You have to be careful in your language here. We're talking about potential energy. They're very similar, but there's just a factor of m difference between them. But just be a bit more careful maybe than I just was with my language there. And gravitational potential is measured in joules per kilogram. Now, the other 2 things we've discovered, talked about so far, little g and big F, they were vector quantities, but potential is a scalar quantity. So there's this slide here, taken from an older book. It does actually show why, in terms of integration, there's a negative sign in the equation. Okay, it's going to end up, we'll do the equation on the next page, but if you look towards the bottom there, you can see that definite integration between limits, and you can see that it comes out to be a negative answer. Okay, so that's the equation there. So again, given to you in the formula booklet, the gravitational potential is minus gm over r. So similar, isn't it, to the force and the field strength equation. Just a minus sign difference, and there's an r, not an r squared, or 1 over r, not 1 over r squared. Increasingly, I find AQA looking more at the graphs. So I think we saw a graph just now of G against r. There's a graph here of potential against r. And if you work out the gradient of that line, we'll find that the gradient of that is equal to little g, or the magnitude of the gradient is equal to little g. I think it's on a later slide. But yeah, there's a lot more focus on the graphs in questions, I notice, over the last few years, whereas there wasn't before, really. And the potential is often in megajoules per kilogram, so as a student or teacher, just be careful about the prefixes there when you're doing calculations. Equipotentials frequently come up in exam questions, and these are surfaces that join up points of equal potential. So no work is done by a gravitational force when a mass is moved along an equipotential surface. Equipotentials are always perpendicular to field lines, and in AQA exams, quite often they want you to draw field lines or equipotential lines, given the other one, essentially. And this fact is really important, that they are always perpendicular to each other, and they don't often use something symmetrical like that. It might be an asteroid field or something like that, which is a lot more complicated to draw. But the main thing to note is that these are always at right angles to each other. Um, and you can imagine them as analogous to things like contour lines on a relief map and things like that. They get increasingly negative is another point that might be worth talking about as well, accentuating that towards the planet or star, the potential becomes more negative. It's more important when you get these weird questions where you've got to predict what's going on in a non-uniform kind of region. So almost there with the equations that are given to you in the book, in the formula booklet now. So we had potential there, potential difference. Now this makes, when you do electric fields, this hopefully sort of makes a lot more sense, because potential difference will be what we sometimes call voltage as well. But in gravity, we call this gravitational potential difference, and there's an equation. The work done moving through a gravitational potential difference of delta V is given by m delta V. So this delta W, or W, is just gravitational potential energy, essentially. Okay, and I try and push that a lot more now with AQA, because they don't give you an equation, or it doesn't seem like they give you an equation for gravitational potential energy, but it's just really this equation here, and you get the potential equation, and you just multiply it by m essentially then to get the potential energy equation. So I think I've written it at the bottom of the slide there. Yeah, so GPE is really this W, or delta W, and if you substitute in for the previous V equation potential, then you could see it comes out like that. And I think students find it useful to see that. When I used to teach WJC, it used to be used in that form actually. So, but increase it, and they never used to ask many questions about gravitational potential energy in AQA, but they've started asking quite a few about it now. So I've slotted that in so that that's not given to you in the form on the bottom left. The work done equals m delta V is given to you, and it's not a huge step, is it, to substitute in for a potential in that equation. But, hopefully that helps. And there's questions here that it's worth doing a lot of questions on potential, because they can be quite difficult for students. This PowerPoint I'll put in a link in the description. So it's a scalar, so it's easy to deal with potential difference. Oh yeah, and this leads, I think the reason I left this, because I've deleted some of the questions from the PowerPoint. This leads into escape velocity, which I'd rather cover this when we do, I think it's the last slide. So that number there for the speed is the escape speed, or escape velocity, but I'll come back and deal with that right at the end. So the potential gradient, I think I talked about this already, that if you've got a graph of potential against R, then the numerical value of the gradient is little g. So there are three equations for little g. Little g is dv by dr, also equal to gm over r squared, and f over little m. So, worth flagging that up. You've got to be careful, or got to be sure about which equation you want to use. Have a look at what other variables are given to you, and then hopefully it'll be pretty obvious which equation you've got to use. This graph I stuck in fairly recently. Then it's that equation. It's that graph again of g against r from right at the start, or near the start. But if a question, they've only asked this recently, I think, that they wanted students to realize that in a graph of g against r between 2 points of r, so delta r, the area under the line then is going to be equal to the potential difference. So it's all using the same variables. You're going to either have a graph of g against r or v against r, and there will be involvement in the other variables. So if it's a graph of g against r, there'll be involvement with v, and if there's a graph of v against r, then g is involved. But the area under the line there in this particular graph is equal to delta v, and in the potential graph, the gradient, the numerical value of the gradient, will be equal to g, minus g technically. This slide just clarifying the equivalence of the two g's that are in the formula booklet, the acceleration due to gravity and the gravitational field strength. So just worth emphasizing that those two units are the same. Newtons per kilogram is meters per second squared, because a newton is a kilogram meters per second squared, and so the kilogram cancels and you're left with meters per second squared. Orbits in the AQA course is fairly simple. In other courses, I think even at GCSE and WJC, you have to know a little bit more of some aspects, but I'll try and emphasize that when I get to them. So a satellite is a smaller mass orbiting a larger one. So the moon is a satellite of the Earth, and the Earth is a satellite of the sun. And we have to use a lot of circular motion questions. It's not always ideal. It's not ideal if you haven't covered circular motion beforehand. When I teach, because I tend to have slightly more lessons than my partner teacher, they often haven't got to the circular motion section when they teach it. So I have to sort of give them the equations to students and roughly describe the terms for circular motion. But it seems to work overall okay. So there will be a lot of equating here, sticking forces and accelerations together, circular motion equations and gravitational field equations. So here we're going to stick together the centripetal acceleration and the gravitational field strength, and we're going to rearrange it to get the orbital speed. So the orbital speed equation is root gm over r. Now that's not given to you in the AQA exam. Okay, so that equation needs to be memorized, and the other equation, the escape speed one, which is on the last slide, very similar to this, and you have to remember it as well. Probably better just to remember the derivation that you have to stick together. I mean, maybe derivation is too big a word for this. You're just sticking together the two accelerations. Or you could stick together the two forces. You could do mv squared over r equals gmm over r squared, and it'll still come out. So this is an interesting equation. It explains, that Jupiter travels more slowly about the Earth than the Sun. Something at GCSE that we might talk about, but we're not really explaining why, and this explains why. Now you can also look then at centripetal acceleration and derive Kepler's third law as well. Okay, so let me just put the whole slide up for a second. I often start off with forces. I say the circular force, so m omega squared r, and set that equal to, equate it with F equals gmm over r squared. The little m's cancel, and then you're left with an expression which you have to substitute in for omega to put the period in there. So omega is 2 pi over t, which again, they might not have come across, so I sometimes teach that a little bit as well. And eventually, with a bit of algebraic manipulation, you get an equation which will basically show you that t squared is proportional to r cubed, which on this particular slide is not that obvious the way it's written out. But t squared is proportional to r cubed is Kepler's third law. All we've done there is square root the t there, so you can see that it's t as the subject. Now this comes up in GCSE astronomy as well, Kepler's third law. I always find it a bit jarring that for the AQA course you don't have to know Kepler's first and second laws, but Kepler's first law is to do with the orbit of planets, that they're in ellipses with the sun at one focus point, and then Kepler's second law is saying that the line joining the planet to the center of the star, the sun, sweeps out equal areas in equal times. Now there's really good simulations and animations about that, so I always recommend that students explore all three of Kepler's laws, because ellipses are quite interesting things, and well, I think so anyway. and there's some nice little videos showing you how you can draw a perfect ellipse with freehand. Well, let's say freehand with some string and 2 marker points. Plenty of things you can find out about ellipses. I think they can still come up in further maths, or at least they used to. But that derivation is part of the course, whether you're either going to start off with equating the accelerations, the gravitational one and the centripetal one, or you can start off with the forces, and the only difference is those m's will cancel. Then you substitute in for omega with 2 pi over t, and it used to be worth 3 or 4 marks, and I think it's only worth about 2 marks now, that derivation, but it needs to be learnt. So here we're going to use, in this particular question, Kepler's third law in a bit, and the orbital speed equation. Now, one thing I haven't come across so far is sometimes another trip-up students make is that the little r, I said it was between the centers, and another way of looking at that, if you're talking about a satellite, it's at a height above the surface, and then there'll be the radius of the planet, or whatever it is, the star. So you have to have both those things added together. So the distance, the little r, is the distance from the center of the star or the planet all the way to the satellite, and it's that's something worth accentuating. So traveling pretty fast there, and the orbital period there, an hour and a half for the was it the ISS there. There's lots of potential for errors of the calculator, I find, in this topic. So worth practicing regularly how to use the calculator with standard form. Really heavy on the standard form, this. So this question here asks to calculate the orbital radius of a satellite in a geostationary orbit, maybe at a period of 24 hours. And lo and behold, it comes out to be about roughly 36,000 kilometers above the Earth's surface, which is one of those numbers. As a teacher, you see it quite often in GCSE questions, satellites being 36,000 kilometers above the surface. Although in this case, we worked out the little r, and that you have to take away the Earth's radius there to get that. Okay. Now, orbits, the geostationary / geosynchronous, you have to be a bit careful here depending on the exam board. So AQA, last time I checked, they interchangeably use geostationary and geosynchronous. But if you're going to be fussy, there is a difference. Okay, I think geosynchronous is the general term. Geostationary is a special case of geosynchronous, but it's not important for AQA, I believe. WJC, I seem to remember, even at GCSE, they wanted you to know the difference, but that was some time ago. Anyway, geostationary or geosynchronous orbits for AQA, I must stress that, you normally get a mark, two marks for describing what they are. So where I would say it's got a period of 24 hours and it remains in a fixed position as viewed from the Earth. The other facts there are correct too, but generally they're the ones I'd use. So roughly a height of roughly 36,000 kilometers. Oh, is that an uppercase K there? And an uppercase M. It's not very good, is it? And they're circular, the orbits, because they're equatorial. Because the Earth is not a sphere, but if you cut the Earth in half at the equator and looked at what you just cut it in half, it would look like a circle. And also one point that might be missed out is that it's got to be orbiting in the same direction as the Earth's rotation. On that diagram, I don't know if you can make it out there, it's also got a low polar orbit. Now, there's so many different orbits. If you type in satellite map of orbits or map of satellite orbits or animation, there's a really good animation online showing all the current orbits of the satellites. There's so many different types of orbit. Geostationary is just one of those orbits. And low polar would be another type of orbit as well. But let's just stick with geostationary for now. If you want to know a little bit more about the differences, that slide will talk to you about it. But for AQA, it's not important, okay? What I would say, if they ask you what is the use of a geostationary or geosynchronous orbit satellite, I would just say communication. You could be really specific, but you could be wrong, because I know some students over the years have written things like SatNav, and SatNav isn't in a geostationary orbit. SatNav satellites, you've got to be careful. You can be quite general and say communication. Now, if you're asked about, I should maybe go back there. If you're asked about a low polar orbit, that has come up in AQA questions, then use of low polar orbits would be mapping, perhaps. Because a low polar orbit, the way it works is it just keeps orbiting the poles and the Earth is rotating, so eventually you map the whole surface. So I would say maybe mapping would be a nice thing to say for that. There's other specific things there, but I went into too much detail on those two slides, certainly for AQA anyway. Now, this is the final section, really, about orbits and energy, which was put into the AQA course in 2015. I don't think it had ever been in there before. A lot of stuff that got put in 2015 used to be in the course, things like dielectrics and things like that. But this, I don't believe, was in the course before, in previous specifications. So, all orbits are elliptical. I mean, a circle is a special case of an ellipse. Going on about ellipses again, but a circle is a special case of an ellipse where the foci or foci are in the same place. Now, this picture here of the sun is really exaggerated for a planet. Anyway, the planets, if you were to look at the orbit of a planet around the sun, it would look almost pretty much circular to your eye. Okay, if you were far distance away. I think I have to check this, but I think both focus points are within the sun. They're not coincident though. So it is an ellipse, as opposed to a circle, which is a special case of the ellipse. And anyway, not to get off the point, the energy of the system remains constant. So kinetic energy plus potential energy must be a constant. And at the closest approach there, the kinetic energy will be maximum. If you follow what I said earlier and look up some of these simulations, there's a PhET simulation, a newish one about Kepler's laws, and you can see in the animations of these things that the planets speed up as they go close to the sun because the force is strongest there. So the potential energy would be a minimum there, okay? And then at the furthest distance away, the kinetic energy would be at a minimum and the potential energy at a maximum. Now, the next slide goes into some equations about potential energy, kinetic energy, and total energy. Now, this is, I think, specific to AQA, so if you're doing another exam board, it might not be in it. You'd have to check. So we've already covered the top left, really. We've talked about potential energy, gravitational potential energy being minus gmm over r. So let's have a look at kinetic energy. So we know kinetic energy in other parts of courses and lower down schools is half mv squared. So let's start off here with equating the centripetal force and the gravitational force. So you've got mv squared over r equals gmm over r squared. Now, the next step, what they're trying to do there is trying to make the left-hand side look like half mv squared. So if you multiply both sides by a half and r, then magically then the left-hand side will change from mv squared over r to half mv squared. And if you do the same on the other side, you get gmm over 2r. So that's an expression, a radial expression there for the kinetic energy. And then the total energy would be the sum of the gravitational and the potential energies, and that comes out to be negative, which surprises some students. And if you draw that in a graph, then you can see that the bottom right quadrant is where the potential energy and the total energy are. As I say, that's something that's been brought into the course in 2015 in AQA. They have asked about this stuff down here. This has come up in recent questions. I don't think they've come up with a total energy question yet, but watch this space, or maybe I just haven't noticed it. Okay, but that's something you won't find in older books and older past papers. Something only really from 2015 onwards. Now I've got an extra slide here just showing you where the escape velocity comes from. There's a really good Kurzgesagt video on escape velocity, really good video. But let's have a little look. So what are we doing here? We're setting the kinetic energy equal to the gravitational potential energy, or I think it normally starts off, you have to move the potential energy to the right-hand side of the equation. So you get half mv squared equals gmm over r. And then you rearrange the equation to get v. And then you get the escape speed, or the escape velocity, is root 2 gm over r. Now that is, you can change that to root 2 g over r, equal to root 2 gr, but most of the time we just stick with that, root 2 gm over r. So this is the other equation that isn't given to you, that's quite important in an exam. So, and it's very similar, isn't it? The other one was the orbital speed, so that was v equals the square root of gm over r. So it's just a difference of root 2 between them. So worth remembering those, but remembering the derivations where they come from. I should say as well that this isn't given to you in the exam either, okay? And this, okay? But in terms of questions, you can lose quite a few marks if you don't remember the escape speed and the orbital speed, or at least where they come from and how to derive them. So I think that's it. That's the end of that topic. And then naturally, generally, people will teach electric fields after this, and then there's a lot of comparison then made between electric fields and gravitational fields. Most of the equations are analogous to each other. There isn't an equivalent of escape speed and orbital speed, but all the other equations are very similar. Maybe I'll do a video next on electric fields. Okay, I hope you enjoyed that. Take care.